In this goal, we are going to be looking at what holds different types of crystals together. It will be a little bit of a review and also some new things. What holds metals together? Metallic bonds. What holds ionic solids together? Ionic bonds. What holds covalent solids together? If you said covalent bonds, you would be incorrect. Remember, covalent solids are molecules, and what holds a molecule to a molecule is an intermolecular force. And our last solid is a network solid. These are held together through covalent bonds. A good example of a network solid is a diamond, and we're going to be talking about them at the end of this goal. Solids come in two different varieties. We have amorphous and crystalline. Amorphous examples would be glass or wax. When you look at their melting point, they don't have a definite melting point, they have a melting point range. And when you go to break them, they don't break along specific planes. They will break in a curve, for example. And that's because there's no real definite structure to the solid. Let's look at a crystalline solid. They can come in atomic, ionic, or metallic arrangements, and they have a more uniform lattice structure. When you go to break these, they break along a definite plane. So if you imagine like a crystal of salt and breaking that salt, you'll have like little squares. A unit cell is the smallest repeating unit of the lattice. And they did take the unit cell portion out of the AP test, but we're just going to mention it here. Crystalline solids, those are the ones that they have a definite melting point. And you can identify that substance because of the melting point. For example, solid water has a definite melting point of 0 degrees Celsius. It has a crystalline structure and it has a crystal lattice. And when it breaks, it can break along a definite plane. These crystals, again, have unit cells, which is a 3D arrangement of the atoms. And here's some examples of crystal lattice cells. And they come in lots of different shapes. So the first two are more cube-like, and the third one there is hexagonal. If you take each of these unit cells and put them together, you get what's called a crystal lattice. So it's kind of like the unit cells are like Lego bricks, and the crystal lattice would be like a Lego wall that you put together. And they come in lots of different varieties. And here's just some pictures of these. The one in the middle, that is sodium chloride, so that's an ionic crystal. And the one on the far right, that is water. And the very first one, that is a network solid that we're going to be talking about with the diamond. The crystalline shapes are not on the AP test, but I think it's quite fascinating. And you can see all these different types of unit cell shapes in these examples. So you can see the cubic or the hexagonal in these crystal shapes. This is a very large crystal of calcite. If you were standing on the floor, this crystal would come up to your waist. It's a ginormous crystal. And I just want you to see if you let these crystals grow and they will follow that unit shape. And it all goes back to the chemistry, how those atoms fit together, but you will have a repeating pattern of each of the unit cells. Let's look at metallic solids. So in a metallic solid, it is held together by metallic bonds. And what a metallic bond is, it's a positive ion in a sea of delocalized electrons. So metallic atoms, they don't share or transfer electrons. Instead, they have delocalized electrons. So that means you have these cations here, and flowing through the cations would be the valence electrons. But this is the electron sea. So you have those cations, and it's called an electron sea model because the cations are imagined floating on the sea of electrons. It is the delocalized electrons that give all the metallic properties. So why can you take a hammer to a metal and bend it? It's because the cations float, and so the metal will distort and bend instead of shatter because the delocalized electrons are free flowing. Why do they conduct a current? Is because if you put a conductivity probe in here, these electrons, they can move. So they can travel up and they can travel down, and they can carry a current. You can still see the unit cell in these metals. Here's some metal crystals that were allowed to grow without being disturbed, and so you can see some of these shapes. Let's look at ionic compounds. So in your ionic compound, its crystal lattice is just composed of the cation, the anion repeating over and over again. In the unit cells, that's where you see these ions. So when they are put together, the negatives are not by each other and the positives are not by each other. They are separated out. But you get this repeating pattern of crystal, and there's many different unit cells, and you don't have to have those memorized. But you should know that the metal ion is the cation, the non-metal ion is the anion, and they arrange themselves over and over again. We don't list how many of each anion and cation we have. Instead, we do the lowest ratio. So that's why this is NaCl, because for every one sodium, you have one chlorine. When you look at ionic solids, some of their properties are that they are very hard, but they're brittle. And the reason why they're brittle is if you take a hammer to them and you slide over the crystal lattice and you get negatives by negatives and positives by positives, they will repel apart. So just sliding it over by one ion, that will cause the whole thing to shatter. And ionic solids, they cannot conduct as a solid. If you were to put a probe in right here, there is nothing to move to go up the probe. However, if you were to dissolve it in water, and most ionic solids, they have a solubility, so they will dissolve in water, and you can see their cations and their anions get separated. And if you put a conductivity meter in, you're going to get your positives go to one side and your negatives go to the other side, and this will carry a current. So this is why you don't want to be in a swimming pool in the middle of an electrical storm, because that salt water that you're swimming in, that chlorine water that you're swimming in, it is a very good conductor. Besides dissolving ionic solids, you could also molten them. That means melt them down, and then that would also free their cations and anions. Ionic solids have very high melting and boiling point, and that's because you actually have to break the ionic bond in order to melt it. Here's some different pictures of ionic solids, so you can see that repeating unit cell structure. Let's look at covalent solids. So in a covalent solid, the atoms are covalently bonded with the molecule. And so, for example, I might have carbon dioxide. Looks like this. So covalent bonds the oxygen to the carbon. And when you put this carbon dioxide as a solid, so here's my dry ice, you are going to get these molecules at the points of the crystal. So it is a crystalline solid, but you have molecules at each of the points. And what is holding it together? Well, in this case, dispersion forces. And that is because carbon dioxide is nonpolar. There are polar covalent solids. A good example of this is glucose. It is polar. It actually hydrogen bonds with the water because we have these little oxygens hanging out that can hydrogen bond with the water. And that is also why sugar or glucose, it is soluble with water because it has that hydrogen bonding with the water. When you take a covalent solid, and if it will dissolve in water, you'll find it doesn't break up like the ionic solid does. It stays together. So a sugar molecule, it will stay a sugar molecule even though it's surrounded by water and dissolved. If you were to boil the water out, you would be left with sugar again. Your covalent solids, they have wide properties. We've talked about dry ice and sugar. This is a wax down here. It's just a carbon-hydrogen chain. Again, also nonpolar, and it is a very long molecule that will have strong dispersion forces because of its shape. These covalent solids, they generally have lower melting point and boiling point than metals or ionic solids. In fact, a lot of the covalent molecules, they've already boiled by the time we get to room temperature. So if you look at like oxygen gas or hydrogen gas, they are gases at room temperature. Hopefully we'll be able to do the lab that's in class, and there will be metallic solids, ionic solids, and covalent solids that you'll be testing. And this is a good summary page for that unknown solids lab. It's called What's in a Bottle. And you will be given samples and have to figure out if it's ionic, covalent, and metallic, and what is the identity of the solid. So you'll be given about 20 solids that they could be, and you'll have to test 4 of them and figure out what their names are based on their properties.